Hey everyone, let's dive right into this explainer and totally transform the way you think about organizing numbers. We interact with numbers every single day, right? We use simple counting numbers to buy groceries, we use fractions to bake, and we encounter endless decimals in complex science. But with so many different types of numbers scattered across the mathematical landscape, how do they all actually relate to one another? Well, whether you're coding software or calculating physics, understanding these categories is absolutely crucial. So today, we're going to build a logical step-by-step framework to sort them all out perfectly.
So, here is our game plan for today. 1. The number sorting challenge. 2. Defining the number bags. 3. Sorting fractions and decimals. 4. Plotting on number lines. 5. The real numbers bag. And finally, 6. Let's practice sorting numbers. Let's get to work. All right, part 1, the number sorting challenge. Picture this. You've got a massive, messy pile of numbers just scattered everywhere. John and Sneha are facing this exact same challenge right now, trying to sort a chaotic pile of numbers, things like 7, 100, -3, and 3/7, into specific labeled bags. And honestly, this isn't just a fun little metaphor. It is exactly how the mathematical number system works. We're basically taking numbers and dropping them into the smallest, most restrictive container they can possibly fit into. But here is where it gets super interesting. These bags, they actually fit inside one another, literally like Russian nesting dolls, building this perfect hierarchy. If a number is simple enough to fit into the very first, tiniest bag, well, it automatically belongs in all the larger bags that swallow that little one up. Keep this nesting doll rule in your back pocket as we build our system. Moving on to section 2, defining the number bags. Okay, we start with bag N, the natural numbers. These are your everyday simple counting numbers starting right from 1. We're talking 7, 10, 100, you name it. Basically, if you can physically count objects in a room with it, it goes straight into bag N. It's the most basic, foundational collection of numbers we have. Now, let's expand that a bit. To get our next category, bag W, the whole numbers, we literally just add one single item, 0. Yep, the ancient concept of 0 gets its very own expansion back. So now, bag W holds 0, 1, 2, 3, 7, 100, the whole shebang. And notice how bag W entirely swallows up bag N? Bag N is sitting right there inside it. Next up is bag Z, representing the integers. To build this one, we take all our whole numbers and just toss in their negative counterparts. So now we're dropping in numbers like -3, -2, and -1. You know, if you owe your friend $3, you're dealing with integers. So bag Z holds all the negative counting numbers, 0, and all the positive counting numbers. And finally, we arrive at bag Q, rational numbers. This bag is a big one. It holds everything from the previous bags, plus absolutely anything that can be written as a fraction. Specifically, any number you can write as P over Q, where P and Q are both integers, and that bottom number, the denominator, Q, is not 0. This is exactly where pieces of a whole, like a half or 3/4, finally find their home. All right, section 3, sorting fractions and decimals. Now that we have our bags, things are going to get a little trickier. Where does an intimidating negative fraction like -13/17 belong? Well, let's just check our rules. Is the top number, -13, an integer? Yep. Is the bottom number, 17, a non-zero integer? Yes, it is. So it perfectly satisfies that P over Q rule and drops clean into bag Q, the rational numbers. But wait, what about -69/1? At first glance, it looks like a fraction, right? So your gut reaction might be to just toss it straight into bag Q. But hold on. Remember our golden rule? We want the smallest possible bag. -69 divided by 1 simplifies to just -69, a clean negative whole number. So its truest, smallest home is actually bag Z, the integers. And you know, decimals can be just as sneaky. There are actually 2 distinct types of decimals we need to look at. First, we have terminating decimals, like 0.12, which just end, stop cold. Then we have non-terminating recurring decimals, like -13.2222, going on forever. But here is the wild part. Both of these actually share a home in the rational numbers bag, bag Q. Why? Well, 0.12 can easily be written as 12/100. And even those recurring decimals, they follow strict patterns that let us convert them into specific P over Q fractions. Long story short,
If a decimal stops, or if it repeats a pattern forever, it is mathematically rational, period. Moving right along to section 4, plotting on number lines. Let's take these numbers out of the bags and put them into physical space. If you want to plot a rational number, let's say 5/3, you just follow 3 simple steps. Step 1, draw your standard integer line. Easy enough. Step 2, look at your denominator. Here, it's a 3. And divide the space between each whole integer into that many equal parts. And step 3, just count the parts starting from 0. Since it's a positive 5/3, we count 5 of those tiny little segments to the right. By chopping up the number line into fractions, you can literally pinpoint the exact street address of any rational number in bag Q.
Which brings us to section 5, the real numbers bag.
Okay, but what happens when we run into numbers that absolutely refuse to play by the rules? We have to compare our neat little rational numbers with a completely different beast entirely: irrational numbers. Rational numbers, as we know, can be written nicely as P/Q. Irrational numbers, absolutely not. No way. These are the wild, non-terminating, non-recurring decimals that completely blew the minds of the ancient Pythagoreans. Take the square root of 2. It's 1.4142135, and it just goes on infinitely without ever settling into a repeating pattern. Pi is another famous one. Because there's 0 pattern, you can never ever write them as a simple fraction. They are permanently locked out of bag Q. So how do we possibly unify our nice, neat, rational numbers with these chaotic, irrational ones? Well, when you combine all the rational bags with the irrational numbers, you create the ultimate master collection, the real numbers, represented by the letter R. Think of the number line again. The rational numbers are packed in there super tightly, but there are still these microscopic, infinitely tiny holes between them. The irrational numbers swoop in and fill those exact holes. Together, the real numbers cover absolutely every single point on that line. No gaps, no exceptions. It's the whole shebang. All right, final stretch. Section 6. Let's practice sorting numbers. Okay, it's time to put all this theory into action. Let's test your new skills and see if you can be the master sorter here. Take a second and mentally place these 4 tricky characters into their correct homes. We've got the number 7, -3, the decimal 0.36, and the square root of 5. Remember the nesting bags? Remember the rules for irrational numbers? Where does each one belong? Let's see how you did. The number 7 is a basic counting number, right? So boom, it lands straight in the natural bag. -3 is a negative whole number, making it a solid integer. The decimal 0.36 stops, it terminates, so we know for sure we can write it as a fraction. That goes right into the rational bag. And the square root of 5? Well, since 5 isn't a perfect square, its decimal expansion is going to be infinite and non-repeating, placing it firmly in the irrational set. See, this totally proves that if you just follow a clear, step-by-step system, literally no number is too complicated to sort. We have completely organized the mathematical universe today. But I want to leave you with one final, kind of mind-bending thought. If the real number line is completely 100% full, stuffed to the brim with rational and irrational numbers, what happens when mathematicians discover equations that point to numbers not on that line at all? If the line is completely full, what wild mathematics lies off the line completely? Just keep that question in the back of your mind as you continue your math journey. Thanks for hanging out with me on this explainer, and keep thinking structurally.